Every time I see it, it still feels a little like science fiction, doesn't it? Watching a massive rocket booster fall from the edge of space and just stick a perfect landing. It's absolutely wild. But behind that mesmerizing magic trick is a literal mountain of complex, rapidly evolving physics. So in this explainer, we're going to dive right in and break down exactly how these returning rockets actually pull off this impossible maneuver, and how, in the process, they're completely rewriting the economics of space.
For the vast majority of the space age, the whole economic model was basically defined by waste. We lived in what's called the ballistic model. This meant building these colossal, multi-million-dollar machines, flying them exactly once, and then, well, dumping them straight into the ocean. But the new reusable model shifts this entire paradigm. It's simply fly, land, repeat. It proves that space isn't just some exclusive place we visit once at an astronomical cost. It's actually a domain we can access routinely.
To really wrap your head around just how absurdly wasteful that early spaceflight era was, think about this analogy for a second. Imagine building a gorgeous, brand-new jumbo jet, flying it from New York to London for its very first flight, and then intentionally crashing it into the Atlantic Ocean. Seriously, that was the accepted, unquestioned norm for decades. Absolute masterpieces of human engineering were just thrown in the trash. The technical barriers to stopping this waste were so huge that the idea of landing a rocket upright on a literal column of fire was dismissed as pure, absolute fantasy.
Well, that impossible fantasy actually became reality in December of 2015. That's when a Falcon 9 booster successfully touched down at Cape Canaveral. And let me tell you, it wasn't just a historic stunt. It was a real game changer. It proved that reusability wasn't just some optional, nice-to-have luxury anymore. It was literally the only viable path forward to survive in this industry. And now, looking at the 2020s, we're watching this mind-bending feat rapidly become just an everyday routine.
So how do they actually do it? To understand the sheer physical mechanics of this return trip, you really have to picture the massive scale involved. For all intents and purposes, a returning booster is a 12-story building falling from the sky. Just imagine that, a 12-story skyscraper tumbling from the edge of space, getting violently battered by wind and chaotic aerodynamics. There is no way, zero chance, that human reaction times are fast enough to manually fly a structure that heavy back to a tiny little spot on Earth.
Since no human could possibly pilot it, the real secret sauce behind reusable rockets isn't just the physical hardware, it's the autonomy. The rocket literally has to act as its own pilot. Its brain is constantly fusing massive amounts of data from GPS, gyroscopes, accelerometers, and pressure sensors. It actually feeds all this data into algorithms that are much closer to what you'd find in a self-driving car than in an old-school spacecraft. The rocket is constantly predicting its motion and correcting its trajectory hundreds of times every single second. It essentially has to transform a chaotic, hypersonic freefall into this beautifully choreographed ballet. And it pulls this off through a very specific sequence. First, it uses cold gas thrusters up in the vacuum of space. Then, the grid fins take over as it hits the atmosphere. After that comes an incredibly violent re-entry burn, and finally, the dramatic landing burn. Let's actually walk through each of these phases step by step, because the mechanics at play here are just wild. Okay, so it all starts way high up, right above the atmosphere. Up there, normal aerodynamic steering is completely useless because there's no air. So in the vacuum of space, the rocket performs this delicate little dance using cold gas thrusters. These are basically small nitrogen jets that fire to quickly rotate and stabilize the massive booster, flipping the whole thing around so the engines are facing downwards. Without this absolutely crucial orientation in the void of space, the fiery drop that comes next would, quite frankly, end in complete disaster.
Now, as the booster plummets and finally hits thicker air, aerodynamic control surfaces actually have something to push against. Enter the titanium grid fins. At first glance, they just look like deceptively simple waffle irons, but unlike flat airplane wings, these fins are incredibly efficient at both supersonic and subsonic speeds. They essentially steer the rocket like a giant fallen dart, fighting off violent wind shear and keeping the whole descent perfectly stable.
And then comes the absolute most violent part of the entire journey, re-entry. The booster is slamming back into the Earth's atmosphere at hypersonic speeds, creating this blistering hot plasma and extreme thermal heating. But instead of carrying massively heavy traditional heat shields that would ruin the rocket's payload capacity, it does something highly counterintuitive. It executes a re-entry burn. It literally fires its engines directly into the oncoming supersonic airflow to hit the brakes and drastically reduce the thermal load. I mean, it is quite literally fighting fire with fire. And the timing has to be flawless.
If it fires too much, it wastes the precious fuel it needs for the landing. If it fires too little, the whole thing risks total structural failure from the heat and pressure.
Which brings us to the grand finale, the landing burn. Now here is a fascinating fact that totally breaks most people's assumptions. The rocket never actually hovers. Actually, scratch that. It literally cannot hover. Even throttled all the way down to its absolute minimum, just one single Merlin engine produces more upward thrust than the nearly empty booster weighs. Its thrust-to-weight ratio stays above 1 no matter what they do. So to land, it has to execute a perfectly timed hover slam. It times its deceleration so insanely precisely that its downward velocity reaches exactly 0 at the precise millisecond it touches the landing pad. Only one engine is firing to keep thrust as low as possible, and those landing legs pop out at the very last second to widen the stance and absorb that final shock. Watching all this technological grace unfold, it naturally makes you wonder, are they achieving absolute pin-drop perfection every single time? When you watch that booster settle onto my pad with that gentle thud, it really looks like a feat of microscopic millimeter exactness. It's almost unsettling, right? Because our mental model of rockets is that they're just big, dumb, unguided ballistic machines. So is it truly a flawless, absolutely perfect landing?
Surprisingly, no, not quite. It really comes down to the illusion of perfect precision versus the reality of controlled error. The software doesn't actually demand a perfect, center-of-the-X bullseye. Instead, it leans heavily on forgiving design. They use a massive landing pad, and those landing legs deploy into a very, very wide stance. The rocket doesn't need to be microscopic in its accuracy. It just uses its algorithms and grid fins to guide itself into a mathematically acceptable tolerance window. It's smart engineering over impossible perfection. So, where is this all heading? Well, the Falcon 9 is really just the opening act of the fully reusable era. Companies are already sprinting toward next-generation systems, like SpaceX's Starship, which aims to be completely reusable, meaning both the massive booster and the upper stage come back. And that system uses even wilder techniques. We're talking horizontal belly flop maneuvers to bleed off speed, advanced heat shield tiles, and absolutely massive aerodynamic control surfaces. The overarching goal across the whole industry is crystal clear: reduce launch costs by massive orders of magnitude. They want to make space truly accessible, make orbital flight routine, and eventually make missions to Mars an actual reality. Ultimately, these returning rockets represent a massive cultural shift in how we relate to space itself. They've turned rockets from disposable, one-off monuments into true, reusable vehicles, much like commercial aircraft. As this technology rapidly evolves with entirely fully reusable systems just on the horizon, it leaves us with one profound question to think about. If catching a falling 12-story building from space is just the new normal, what impossible barrier is the space industry going to shatter next?